Michio, Kaku, Beyond Einstein, The Cosmic Quest for the Theory of the Universe. The transistor, laser, and quantum mechanics. The consequences of quantum mechanics are all around us. Without quantum mechanics, a plethora of familiar objects such as television, lasers, computers, and radio, radio would be impossible. The Schrödinger wave equation, for example, explains many previously known but puzzling facts such as conductivity. This result eventually led to the invention of the transistor. Modern electronics and computer technology would be impossible without the transistor, which in turn is the result of a purely quantum mechanical phenomenon. For example, in a metal, the atoms are arranged in orderly fashion in a lattice. The Schrödinger equation predicts that the outer electrons in the metal atoms are bound to the nucleus only loosely and in fact may roam freely throughout the entire lattice. Even the smallest electric fields can push these electrons around the lattice, which in turn creates the electric current. This is why metals conduct electricity. For rubber and plastics, however, the outer electrons are more tightly bound, and there are no such free roaming electrons that can create a current. Quantum mechanics also explains the existence of materials called semiconductors, which can at times act like conductors and other times like insulators. Because of this, a semiconductor can be used as an amplifier to control the flow of electricity, like a water faucet where the flow of water. Invention of the transistor, Nobel Prize, 1956, John Bardeen, William Stockley, Walter Brattain. Quantum mechanics spawned another invention, the laser, currently altering the way we conduct industry and commerce. Quantum mechanics, first of all, explains why neon and fluorescent lamps work. In a neon light, an electric current surges through a tube of gas, energizing the atoms of the gas and kicking their electrons upstairs into a higher orbit or energy level. The electrons in gas atoms, which are now in an excited state, would like to decay back to the original state of lower energy. When the electrons finally do decay back into a lower orbit, they release energy and emit light. In a light bulb, the excited atoms decay randomly. In fact, all the light around us, including sunlight, is random or incoherent radiation, a mad jumble of radiation vibrating at different frequencies in different phases. However, physicists such as Charles Townes of the University of California at Berkeley use quantum mechanics to predict that in certain cases the excited atoms could be made to decay at once in precise synchronization. This new type of radiation, called coherent radiation, had never been seen before in nature. In 1954, Townes and his colleagues successfully produced a pulse of coherent radiation, the purest form of radiation ever seen. Although Townes' pioneering work was for microwave radiation, he won the Nobel Prize in 1964. Scientists quickly realized that his theories would work for light as well. Although Buck Rogers type ray guns and beams that can blast incoming nuclear missiles are well beyond our present capability, commercial lasers can be used to cut metals, to transmit communications, and to perform surgery. And newer applications are being discovered daily. Doctors, for example, are using mini lasers to send light energy along fine glass wires to burn out fatty deposits in the veins of people likely to have heart attacks. Laser discs have changed the way stereo recorders are built, and many supermarkets now use laser light at checkout counters to read instantly the black line barcodes seen on the packaging of most products. Perhaps the most spectacular commercial application of the laser would be the creation of three-dimensional television. Already, Visa cards are being issued with a hologram image of a three-dimensional bird. It's conceivable that in the future our television screens, instead of being flat planes, will be three-dimensional spheres in which we can see three-dimensional people moving about. Our children and grandchildren probably will watch three-dimensional television in their living rooms, complements of quantum mechanics. In addition to the transistor and the laser, hundreds of other important discoveries owe their existence to quantum mechanical effects. To name just a few: 1. Electron microscopes. 2. Unlocking the DNA molecule. 3. Fusion machines. Electron microscopes. These exploit the wave-like properties of electrons to see objects to the size of viruses. Millions of people have benefited directly from the enormous medical applications of this quantum mechanical invention. Unlocking the DNA molecule, X-ray diffraction and other probes are used to determine the structures of these complex organic molecules. Eventually, the secret of life itself may emerge from a quantum mechanical study of these molecules. Fusion machines. These will use the nuclear reactions of the sun to create enormous amounts of energy on the earth. Although there are still many practical unsolved problems with respect to fusion machines, eventually they may provide a virtually unlimited source of power. Without question, the success of quantum mechanics has altered the foundation of medicine, industry, and commerce. The irony is that quantum mechanics, which seems so definitive and clear-cut in its practical applications, actually is based on uncertainties, probabilities, and philosophically bizarre ideas. In short, quantum mechanics dropped the bomb on the world of physics, and the effects were shattering. Anyone who is not shocked by quantum theory, proclaims Niels Bohr, has not understood it. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. In 1927, Werner Heisenberg proposed that it's impossible to know the velocity and the location of an object simultaneously. He proposed that it's impossible to know the velocity and the location of an object simultaneously. You can't know the speed, velocity, or the location at the same time. Why? A wave, after all, it's a smeared object. If we're standing on the beach, how can we calculate precisely the velocity and the location of an ocean wave? We can't, according to Heisenberg. One can never know precisely the position and velocity of an electron at the same time. This is also a direct consequence of the Schrödinger equation. According to Heisenberg, this uncertainty arises because in the subatomic realm, the very act of observing an object changes its position and velocity. According to Heisenberg, this uncertainty arises because in the subatomic realm, the very act of observing an object changes its position and velocity. In other words, the process of taking a measurement of an atom system disturbs the system so greatly that it alters its state, making the system qualitatively different from its state before the measurement was taken. For example, an electron is so small that to measure its position in an atom, photons of light must be bounced off of it. However, the light is so powerful that it bumps the electron out of the atom, changing the electron's position and location. However, one would argue, with a better measuring apparatus, couldn't the velocity and the position of the electron be measured without altering it? Well, according to Heisenberg, the answer is no. Quantum mechanics asserts that we can never know simultaneously, no matter how sensitive our measuring devices are, the exact position and velocity of a single electron. We can know one condition or the other, but not both at the same time. And this is called Heisenberg's uncertainty principle.